So this is the, I guess, second in a two-part video series on the design of an HVAC system for your project in Environmental Systems 2. Last week we talked about this assignment where we were looking to find a peak heating and a peak cooling load. And then there's a pretty long video related to that in which I talk about different versions of this model that and this model is of the Asheville Middle School, which was the case study we did last week. And so we talked in some detail about why peak heating loads and cooling loads are the sort of baseline piece of information we need to size our system. We talked about different ways we could model this and how it's really just, in a class like this, it's not important that we're accurate. I mean, we'd love to be, but this is more process. And in the end, we talked a little bit about space use zones and why you might want to not have a single space use that you design for your whole project or that you establish for your whole project. And so let's just talk about that for one more second here, or one more minute. In my project, all of these, so most of this side of the southern side of the building, for example, is classrooms. And so if I go to, if I select these zones, or these, they're zones, I'm sorry, and I can see that they're all set as classrooms. I open that up and I can look at what the template settings are for classrooms. We have a fair number of people, which makes sense. We have very high equipment use, which I think also makes sense. Lighting is typical, but still pretty high. A low target illuminance, which I'm not quite sure why. It's interesting. We have high mechanical ventilation for both the building and for the room, and I think I understand why that's true. So the point is that we can use this to both try to make our model accurate, but also to learn about, because this is from the Energy Code, basically from ASHRAE 90.1, and it's giving these are pulled from that pretty complicated standard and given to us in this form, so we can look through it and try to understand what's going on, and then adjust it if we think we know that we want to, because it's always going to be more accurate if we're intelligent and knowledgeable what we come up with for our own project than some generalization. Not always, but very often. But let's, as just a capstone on that, so let's look at another zone. And by the way, and so these are all from this is rough modeling from the plan set that I have of the project. So this is a science lab. And there is a science lab template, 90.1. And let's just see if we can see what the differences are here. First of all, less people in a lab than in a classroom. Interesting. Not quite sure why that would be true, but it does make some sense. Equipment loads very high, and lighting also. That makes sense in terms of what usually happens in a lab. Then in conditioning, we have no fresh air for people, but a very large fresh air for the building itself. Like it wouldn't be that kind of a baseline would be 0.06 for this, or maybe 0.12. So this is clear that this is a space that we need to flesh out very often, and it makes sense. We're in a science lab. We're doing experiments. There's probably a fume hood, so this is a general setting to take into consideration that that amount of air transfer. And of course, we talked in the last video about how then, in a peak heating load situation, that means we're going to have more air moving out of the building that we've conditioned. Now, hopefully we'll have some kind of energy recovery ventilation, but we're going to lose heat there, so that's going to raise our peak heating load. All right, so that's why you would go to the level of space use zones to learn, and also then to, this might help me understand how I want to lay out my project, or how I want to consider my HVAC system design, because I'm looking at the project. I already know it, but I'm looking at it in 3D. I've got these zones. They're color-coded, and I can think more about, like when I look at this, I think, yeah, that I understand why the engineer chose a centralized system, and it has to be that you have, because this is where the boiler room is right here. You have a boiler in here, and then you need to have either water or with a boiler, it would have to be water, but something that's very small and can move all of it because you need to get water to here, 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 way over here from this one source. Um, and then you can insulate those pipes really easily. It's an efficient way of getting that heat to a position. Once there, though, it's a school. I can see why then they said, let's now bring in outdoor air and heat and cool that air and supply fresh air through air so that we have a simpler system. It's just, we can just plunk down these mechanical AHUs on the roof wherever we need them, go straight down with our supply and return ducts. It's a pretty straightforward, and this is a utilitarian building. It's a school. We have a lot of roof area. It's not like that people can see it or need to use that part of the building. So it makes sense to me why they did that. Okay. You may remember that we then we did a variety of different versions of this building and different runs from simple and more complicated. One that kind of I almost think it was just to some degree luck. I mean, I did my best to model this, and I know something about this, and I can tweak it and adjust it to in ways that help make it accurate. But this run, and actually I think it was, let's see, this is, I ended up using this simplified run. Oops, I should turn that. Sometimes it takes a while for these to turn off. Yeah, so let me go. I only had a single space use setting for this, or a whole building zone. Look in the previous video if you don't know what that is, but this came out to be quite accurate. So I'm just going to use the outputs from this run. And why do I say they're accurate? Well, my peak cooling load peak heating load is about 5,000, 4,900, and the engineer set it at 5,000 for the project. The cooling load's 392 tons, and mine is 450. So that's for this level of modeling, that's really accurate to the what the engineer actually just determined. So just making the point that we can't. This is useful, and it's way better than looking it up, in my opinion, in a chart in Architect Studio Companion. But okay, anyway, now we have these numbers, and that's all we needed from last week in order to start sizing our system. And well, first of all, use this to decide how we might want to, what type of system we want to use, and then from there size and lay it out. I'm going to start just saying we're gonna go with the system for this particular project, since that's what we modeled. I already know what the engineer did. Is what I just described. It's going to be a single source of heat and cool, and then that being distributed through a bunch of zones. So our peak, we only need a single peak load and a single peak for the entire project for heating and cooling. So I have a spreadsheet that I've created to allow you to size. Let me show why that's in there. So let's just dive into it. I'll in a minute talk about the peak cooling heating design. It's really, well, anyway, I won't. So these don't actually play into the calculations. This is like the typical spreadsheets I make. Blue is our cells you enter in. Yellow or whatever color you want to call this, have equations in them. So you don't want to mess with them. I don't know if they're locked here or not, but if you do mess with them, you can just reopen up again. Oh, and then red is a constant, or this light red. So what we're doing here is we are determining the amount of air we need to move. And in this case, we are moving heating, cooling, and fresh air ventilation in air. So we need to find which is more, the amount of air we have to move for heating, peak heating, or peak cooling, because it's in the same duct. So we just need to know which is the most. and then we'll add to that the amount of ventilation, fresh air we need. So we're talking about moving air to, you don't really need to know the details of this, but if you think about it, we're going from Q, which is heat or energy, kilobtus per hour, and then we need to know how much air we can move. We need in order to move a certain number of kilobtus per hour. So we need a constant, which is what this 1.08 is, that allows us to determine how much heat a given volume of air can move, like a unit of air. And here's an equation down here saying how that works. Okay. You can ignore that if you want to. Let's just dive right into it. So my peak cooling load is about 450 tons. So 450 tons. And that's automatically converted to kilobtus. Now you remember that a ton of cooling is 12,000 BTUs or 12 kilobtus. So often you'll see cooling equipment defined in tons. It'll also be in EAR or SEER. We talked about that. Okay, but so we're saying I've got 5,400 kilobtus of cooling peak, and my heating peak was 4895. I'm even just going to put in 5,000 because I'm not trying to feel like I'm super accurate here. Okay, and that's in kilobtus. Okay, so now we have our peak loads in. What else do we need? Well, let's think about this for a second. So we're trying to heat or cool a space. So we don't just need to know the amount of energy we're moving. We need to know something else about the air, and that is these. And by the way, all these variables are clearly defined over here. We need to know the supply air temperature and our set point. So for cooling, I'm going to go look in the case of this project. They gave us. I don't think you should use these. This is for a school. I would probably use 68 and 75 or something like that, or you could just use 65 and 65. Whatever you think that and it's probably going to be different for different parts of your project. But the idea is that you don't always have the same set point, because in the summer, the set point's usually higher because people usually are wearing less clothing, and you're just acclimated, and so in the winter it's a little bit lower. But wait, what am I looking for? I'm looking for this. Their set points were 72 and 75 in the plan, so I'm gonna set it to that. So I'm gonna say my cooling set point is 75, and my heating set point is 72. So that's what I want the room to be heated or cooled to. I also need to know then what is the temperature of the air that I'm moving. I need to move this much, these many BTUs, but I need to know what temperature the air is that I'm moving to know how much of it I would need to move those BTUs. So the rule of thumb is 55 degrees for cooling, and I'm going to say 100 degrees for heating. I noticed that well, I actually want to get into that. You often will see 100 to 120 for that number. I think. Let me just go ahead and. Let me see if I did see this correctly here. Now I remember what I was looking at. It was we talked about this in the video last week. In the I think the default when you run these simulations is 95 degrees for the maximum supply air temperature and 53.6 for the cooling supply. So maybe I should use those since that's what the simulation was run on. But again, it's not that 53.6 is kind of little. But let's just do it. 50. And that's probably a conversion from metric. And then over here we were saying 95. Okay, so now we have a total CFM, and this is the reason we have to go through this process because um, we can see that we had a well, in this case, we have a higher cooling CFM load, and also our CFM, our cooling CFM is the highest. It could be that, let's see if we change this to, no, of course, that goes the same direction. Um, the point is that it's the fact that we have, I'm going to change this back. I'm going to change it back to, I like 90, I like 155. It seems clean to me. Anyway, what's the point here? That the difference between our set point in cooling and the cooling temperature is 20 degrees. The the difference between the heating set point and the supplier temperature is almost 30 degrees. So we're going to be moving a lot more heat per unit for CFM per cubic feet of heating than we are of cooling. So that's going to make it to where it's our heating air distribution is going to be more efficient. Now, if that's confusing, just realize all we're saying is that we want to pick the largest of those two numbers because that's going to determine how big our duct needs to be. Okay, so we're done with that. We're going to say that we need 250,000 CFM total for the project. But that's just for moving heating and cooling. We also need to move fresh air. So, and remember that, that's part of the question is how much additional air do we need, coming in through our, oops, through our fresh air ducts and our AHU on the roof. So let's just, I'm going to go real conservative here. 175,000 square feet is the size of our project. Now, there's no way that we're ventilating for people in all those places, in all that square footage. We've got corridors and mechanical rooms and lots of places where people are not hanging out and that we need to ventilate for them. But okay, but we need to know the amount of area we're talking about. We need to have an amount of people. No, I'm sorry, an occupancy. And this is occupancy per square foot. So I'm going to put in, this is a number that I see a lot. This is not, so we're not putting in like the occupancy numbers for egress. That's going to be like the maximum because you're saying if we have the maximum people in this classroom and there's a fire, we want to be able to make sure everybody gets out. This is for the ventilation you need for general use of people in the building, and so we're not going to create ventilation capacity for some really high amount of people. Then we have to decide. So this is how many people we have per square foot, and you can just go ahead and use that number. Then we have to have. So now we have to know the ventilation rates based on the space type we've got. Now you'll remember if you look back in my zones here, I think we set this at 10, just generally. Yeah, 10. That's pretty high. But and you can go and look at in the slides. We have those pages from the ASTM standard that talks about this. And so classroom here, right here is 10. And 0.12 for the. So remember, there's two numbers here. One is how much air we need to bring in for people, so that they can breathe and not die. And the other is how much do we need to ventilate the building, like in terms of if there's off-gassing from products or there's things happening like in that science lab that we need to take out. So we're going to put for this number 10 and 0.12. Yeah, and this is supposed to be, I'm sorry, 0.0125, I think. Because, let's see, 1 divided by 0.0125. That's about 80 square feet per person. So we're saying on average for the full 175,000 square feet, there's a person for every 80 square feet. In a school like this, that's a lot of people. So that seems accurate to me. The point here, even though, okay, this may be high, I'm just trying to do an example, is that this number for fresh air is way smaller than this number, which is our peak cooling load. So fresh air ventilation, um, I'm going to say always, always dangerous to say always, but always is a smaller amount of CFM than if we were moving heating and cooling in the air, and so therefore the ducts are going to be smaller. Um, that might be a reason why you would decide not to use an all-air system, because you want to have a nice open CLT ceiling in all your floors, and you don't want to have a bunch of ducts up there. If you could design it to where you're moving heating and cooling not in ducts, like in refrigerant or in water, and then just have smaller ducts for ventilation, that would save you space, and you could, that might fit your architecture better. In this case, though, we're doing both. So we're adding and this is automatically is an equation that does this for you. It takes the largest of these two plus the fresh air. And so now we've got 292,000 cubic feet but that of air we need to move in our supply ducts, and that's going to have to come back in our return ducts. What do we do with that? Well, there's a bunch of different calculators out there. I just chose this one. There's a link to it here. Couple things you have to set up, and then it's pretty easy to use. Make sure you're in US units, not metric units. You could try different materials. The duct board's fine. We can talk about what these are. They're just different ways of different materials to create ducts. The ducts are built out of. You need one more variable. So, well, actually, of course, first we need the CFM. What was our CFM? 292. So 292,000 CFM. And then we need to have one more variable. So pick friction loss, 0.1. This is just saying how much there's going to be a little bit of loss in CFM velocity from rubbing against the ducts. So we hit calculate, and we see that we have 110 by 110 for a rectangular duct. Now, there's other things we can do if we wanted to actually do a design for a single supply, like if we had a peak load for a specific zone, we could limit the height of our duct, and then it would tell us what the width would be. But we're using this to get a total. So I'm gonna multiply 110. Oops. 110 times 110. So I'm gonna square it, and then divide by 144, because that's how we get from square inches to square feet. And we have about 84 square feet of total trunk duct for the project. What does that mean? So didn't we say we had like there were, I don't know, 15 of these AHUs on the roof, and each of those is going to have a trunk duct. I think there might even be a couple more because the gym, I think, has some, but let's just say it's 15. And so if we said, what was our number? 84. So if we say 84 divided by 15, let's just say 6 feet. So that's 6 feet cross-sectional area, so length times width, for each of our trunk ducts. So if we go back into our little summary in the slides, this is from the drawings, right? We were saying that we have this layout here where we've got the HU on the roof, branch and supply ducts coming down. Trunk ducts, which is supply and returns, coming down in this chase, and then they're branching off. We're saying, and then so there's actually supply. We're saying that each of these supply ducts going down is about 6 square feet. Is that what we said? Make sure. Yeah, 6 square feet. So 2 by 3. Now that seems a little small to me, maybe, but maybe not. These aren't really huge zones, but it's definitely reasonable. Um, and that's what we're doing here. We're saying, okay, we have now um, taken our peak loads, looked at our supply temperatures, our set points, brought in our ventilation load, and got a total CFM, then use that to size to get a total supply duct size, and then we checked it and said, yeah, it seems like that makes some sense. It's 84, so I'm going to put the 84 square feet here. Then you see we get automatically 100 feet for the branches. Now think about it. So that's a rule of thumb. I think it's 1.2 times the trunk. So the trunks and the branches have to be carrying the same amount of air. That's kind of obvious, right? And it has to be balanced. You have to take the same amount out as you're bringing back in returns. So what's the relationship between the trunk and the branch sizing? The branches have to be larger because since they have there's more of them, so they're going to have a smaller diameter or cross-sectional area. That means they're going to have more friction. So we need more cross-sectional area to make up for that friction, so about 20% more for the branches. So that's where we get that. Okay, so the one thing I didn't say here, though, so that's the duct sizing, but we also have our equipment sizing, right? So we know we need to find a piece of equipment that can deliver 450 tons of cooling or 5,400 kilobTUs of peak cooling. We have to find a boiler, if that's what we're using, that has a peak output of 5,000 BTUs. By the way, if you want to get technical about this, remember these like a boiler is not 100% efficient. So if we need to deliver 5,000 kilobTUs, we really need to have like a 5,000 times 1.2 probably if it's an 80% efficient boiler. So it needs to be bigger than that a little bit. I'm not worried about those details. I'm just letting you know that this is why we have engineers. This gets really complicated or very detail oriented, and we're just trying to get the overview and get something that's that we've thought through and we feel like we grasp. Now, where would we get these? Remember, I want you to start looking for equipment because you get so much information if you access companies that are selling you this stuff. And so I did that in the slides. I went and I showed us that we have, for this project I'm saying, we have, they did their calculations. We talked about this last week, and then we had equipment schedules there's numerous pages of these. I pull out a sample, and we have specifications for a specific. We have a Train RTA E200 water chiller. We have a Lochinvar boiler, a specific boiler. We have this. This Train CSAA is a sort of a package that you buy, and you can configure how you want to. So we can look those up, which I did, and I found these manuals for them, and I posted them, and they're in the resources section of Canvas. And you could, if you're using a boiler and chillers, you could look up, you could use these documents and find the right size for what because there's a bunch of different sizes in all these documents. This air handler book. I'm going to open it up. Take me a second to find it or to access it. Sorry. Where am I here? So, for example, this is like a whole book about air handlers and how you can set them up. It's bookmarked. So there's all sorts of information on basics. There's you've got similar graphics to what we've got in our slides. So they're really teaching you about how they work. You've got a bunch of different layouts that are possible that they're showing you in graphic form. So why wouldn't you access this and not only get sizing for some equipment, some pricing, but also a lot of information? And and probably models. They probably have Revit models of these things that you can use, or so trying to get you in the habit of doing that. You need to get a size for your equipment, and you need to know where you're going to put it. And so we could do that with this. We could have chiller, a boiler. We know our ducting. We've said if it's we could make it flex or box duct that's rectangular. Okay, so that's the full process. Then you would lay it out, right? And you'd have to then say, okay, I'm going to take my 2x6 duct, and I'm going to make a chase. There's going to be two of them in there because it's supply and return. I'm just mimicking what I see in this design here that we were just looking at. And lay them out. Read the instructions on the assignment. We're looking for something very basic here. I'm not saying this is a completely different assignment here, but I include these to say, hey, you can get screenshots from your model. You can draw on top of that. You can, down here, for example, really basic sketches. Look at the three sets of drawings that we've given you. There's a really nice schematic in the first, as an example, in that first set about the Sure House, that solar decathlon house. So not looking for taking stuff out to Illustrator and doing a bunch of line weights. We're looking for sketching on top of things that you can screenshot. And the main thing is to get some clarity so somebody looking at it can understand where the thermal energy is coming from, how it's being distributed, where the fresh air is, something about sizing, right, and loads. We went to all that trouble to get these numbers. We need to include those in this. Okay, so the final thing I want to talk about then, and it's described in this assignment to some degree. So always read the assignment. I do my best to make these as clear as I can, and clearer probably than when I'm, by the way, like I mentioned in the last video, I've been sick for a week, so I'm kind of spaced out. Hopefully this has been somewhat clear. But okay, so what most of you are doing your projects from last semester, which were apartments, right? Like a number of apartments with some public space, like a lobby and maybe workspaces and a gym. I don't know what you had in there. If you think about it, the approach that we're using for the Asheville Middle School would probably be difficult to do in an apartment because it's centralized. And how are you going to separate this out to individual apartments in a way that, first of all, there's a lot of them, and so that would be complex, but also in a way that people can pay for their own heating and cooling. Maybe that's just included, and they don't. So I'm not saying you can't have a centralized system, but you might want to do something more like what the project that we're doing or that we did this week, the Candela Apartments, that has heat pumps and a centralized air column for individual ERVs in each apartment. You could do that. You could do even just single mini splits, really simple with like a ERV that's sitting on the exterior wall for each apartment. So there's you could really do it with probably no ducting or very little ducting. Or you could do some kind of combination. You could do heat pump systems to the apartments and then a more centralized system like we were just talking about to the lobby and the public areas. If you were doing it that way, then you could just do a full layout for the public areas, which would be pretty simple, not that much more than what you're seeing here in these little sketches, and then maybe do a single apartment, or maybe if you have two different kinds of apartments, one you think is going to have need a bigger heat pump and have one's got ducting and the other, a cheaper apartment, doesn't have ducting, it just has a mini split on the wall. You could do both of those as examples. Draw single examples and then number them, and then just say on your plan or your axon or whatever, 1, 1, 1, 1, 1, 1 for all these apartments, 2, 2, 2, 2, 2, 2 for all these apartments, and then have the little sketches on the side, so that we know, so that we get a feel for the full design. So how would you do that? Let's say you wanted to do this where you had some mini splits. So you can be playful here. I mean, you can be a little bit loose. So let's just say we were looking at this project and we did it. Remember, it's so easy in Rhino too. I can get I can get volumes So that's the full volume of this project, and then I can get volume of individual spaces really easily. So if I wanted to know the volume of this full project and then the volume of this section, I could get those two numbers really quickly and divide one from the other and say what percentage of my peak load was coming from that smaller portion of the project, right? So let's say I figured out that half of my square footage was apartments. So I'm going to divide that 450 there by 2, so I'm going to have 225. And then I have, let's say I have 50 apartments. 225 divided by 50, that's 4.5 tons per apartment. And then I could use that here. And now, this, by the way, this is, designed for not this exact purpose, so maybe these totals don't help you. You don't have to make this a completed spreadsheet that you would turn in. What you do want to use this and have clear, outputs that you can include. Then these would be the same. Now we're getting CFM, and okay, over here, we would probably convert this to tons, or we'd have to look at what the we wouldn't really need to. If we do this again, 5,000 divided by divide by 2, and then divide that by, did we say 50? Nope, I did something wrong there. No, 9. So maybe we have 9. That sounds high. I didn't keep track of the numbers, but oh, maybe it was 9. Whatever. We would find a number here. So let me just do it again. 5,000. What did I say? 5,000 divided by 2. I wasn't paying attention. Clear that. 5 divided by 2. 2,500. And then I think we said 50 apartments. Oh yeah, so 50. So 50, that's definitely 50 kilobtus would be the peak. And then these are our, so we could do the same thing, and we could get for an individual apartment. Of course, we do the same thing here for the ventilation. We could get an individual duct sizing if we wanted to duct it, or if we're just doing fresh air, that might be another way of doing it. So then we could just use this portion. So my point is that we can then pull out parts of the project and use this spreadsheet to size individual portions, and then pull it together into a complete design. As is described in the assignment, right? So giving you tools to be able to rough this in and then deliver something that's much more defensible than just, a box that says HVAC and, no ducts, which is what I see a lot of the time. Okay, that is it. I will see you in class or in another video if you're not in my classes, and let me know how it goes.